In this video, I will introduce you how to use our TALOS robot at LAAS with ROS control and gazebo. So you can prepare your experiment on the robot display on the left with gazebo, and this simulator will provide you position and torque control. As a sensor, you're gonna get torque measurements, and all the software infrastructure is fully open source. Therefore, you're gonna get the whole body dynamical model open, which include the initial parameters, the length of the links, center of mass position, and so on. All the codes are available on GitHub under the PAL Robotics entity, and you have the links here on the bottom. There is also another simulator which is available at LAAS and provided by PAL Robotics, which is much more realistic. It provides you torque control, torque measurement, but it is closed source. And the reason why it is because it integrates the controlled actuator model using a frequency model, and this allows you to be much more close to the robot, including some of the bandwidth limitation of the robot. Because it's not gazebo, the visualization is done through AirViz, as you can see on the left. However, there is an easy integration of an API which is building on top of ROS control. Let me introduce briefly ROS control. So first, you have a robot abstraction called an hardware abstract layer, providing different way of controlling your joint. You can control it on effort, velocity, on position in a standard way. And you can have access also to the sensor, such as force torque sensor, the specificity of the implementation of PAL, and an EMU sensor. Now you also have a controller abstraction, and on using this controller abstraction, several controllers are provided. What is interesting is that those controllers, you may already know them because they are used for a lot of robots. They can be changed through configuration file. So you have effort controllers, position controllers, and the most famous one, joint trajectory controllers, which are used to do trajectory following and which can be the product, for example, of MoveIt or another motion planner. Then we have what is called controller, but which is in fact observer, and we have the standard joint state controller giving you all the joint position. So how ROS control works, it implements an hardware interface for the specific robot, so here TALOS, and all the real hardware access, all the simulator to the IMU encoders for sensor icons are hidden by the method read, which will call the sensor and feed the internal variables of this object. Then there is an update loop called in a real-time operating system. So in TALOS, this is a RT preempt patch of our Linux. And this update will call a set of controllers which will interact with the hardware interface through the API that I described previously, which means the IMU sensor interface, the position joint interface, or the effort joint interface. The controller will then compute a command, specify through this interface, which will change internal variables. Then those internal variables are wrote and sent to the motor, again in a very in a way completely hidden to the user, which do not care if you're in the control side. Now the controller that you have in yellow on the right, they are loaded through ROS services, which are specified in green on the complete right of the slide. List controller, load controller, onload controller, and switch controller. Here you have an example of an advanced controller, which is our own hierarchy of inverse kinematics, which allow us to switch between, on the left, the real robot or gazebo on our computer. Again, everything is done through the interfaces, and what we have done is we have implemented our own ROS controller. And on the right, sorry, you have the graph of computation that we are using in LAAS and which will be described later on. The same way, we have another controller called TSID using weighted QP, but it is independent thanks to the ROS control subcontroller, which is making the propagation of the control compute by architecture to the ROS control system. You can build your own controller here, this way, which can be run either on the real robot or the PAL simulator or gazebo. What we are providing at LAAS is a software development kit that we call the stack of tasks to implement a whole body controller. It is composed of a dynamic graph, which is a C++ library able to handle a graph of computation for control in a similar manner to Simulink. Of course, this is optional. You can also use Pinocchio, which is a template-based implementation of the Featherstone spatial algebra, which is extremely useful for rigid body mechanics. And Pinocchio is extremely efficient. Then, on top of this, you can use two kinds of solver. One which is a hierarchical inverse kinematic solver, and the other which is a multi-objective quadratic program, which is rather classic right now, to perform whole body control in torque or in acceleration. Let me briefly introduce our dynamic graph. So here we consider on the left a robot, which is basically providing measurements of the encoders, which are fed to a dynamic computational node, and this node will compute a homogeneous matrix that we called here M. This is not the mass matrix. And this homogeneous matrix, which give you the current, for example, position of an net effector, such as the feet of the humanoid TALOS. On the other side, we are providing a walking pattern generator, which is generating a desired feature that we will call M star, which is another homogeneous matrix, but the one that you would like your robot to follow. So what does the feature? It computes the difference between your desired feature and the current one, and it also provides a Jacobian of this feature. It is then used by the task, which is imposing a dynamics on the regulation of the error, which here it's an exponential decay, which can also take into account the fact that your desired feature may change over time to do trajectory following or trajectory tracking. So once you have decided a set of tasks, we have our hierarchical QP, which is able to project into the null space of the task of higher priority, the other task of lower priority. And then this creates a Q dot of minimal norm, which is then integrated and sent to the robot. And finally, we have TSID, that is explained briefly here, which is a weighted multi-objective function. Multi-objective optimization, where we assume that the robot has to perform n tasks, each defined by a task function, and the control variable, which are called here y, I, are the velocity of the actuators, the forces, the external forces, and the actuating torques. So based on that, for each task, by linearizing them, you have this set of linear task function that we call GI. And what we do is we try to minimize the weighted sum of this quadratic error specified by GI and subject to linear equalities, where we can put some of the tasks if you want them absolutely to be of higher priority, and the dynamics of the system. More information can be found on the website of Andrea Del Prete, who wrote and who is currently maintaining TSID. Thank you very much, and I hope that you have enjoyed this small tutorial. If you have further questions, do not hesitate to contact me. Thank you.